I'm Phil Maechling. I'm an associate director at the Southern California Earthquake Center that we call SCEC. I'm the presenter here. I'm going to describe work that a group of us at SCEC have been doing on blue waters. I want to point out before I start that there's a lot of other earthquake research going on at SCEC. We have a broad program, basic research, development of research into seismic hazard products, as well as education and outreach activities. And I won't cover all of an overview of all of SCEC, of what SCEC is doing. And today I'll just focus on work that we've done recently this year using blue waters. So our primary kind of goal and activity over the last year was to calculate a probabilistic seismic hazard model for Northern California. And so that's the work that I'm going to talk about. So if I read the presenter guidelines for this symposium, it asked us to early on, one of our first slides, to address this, how we use blue waters. So in very simple terms, the way what we do on blue waters, we calculate accurate ground motions up to 1 hertz for any site in California for most possible earthquakes. So that's a type of earthquake research, and it may not be what you kind of expect. It's not predicting when earthquakes are going to happen, but it's in some sense saying if an earthquake does happen on a fault, what is the shaking at places that I'm interested in? And this is the key question. It's site-specific. We want to calculate what are the ground motions at sites of interest, where people and industries are particularly interested. So another way I like to think about this is, let's say, the success criteria for our research. Is there at any point that we could say where our research is successful, we're done, and no further advances are needed? Well, it might be this. So in casting this as our kind of a basic research challenge, our aim is to calculate accurate ground motions at any site on Earth for any possible earthquake. So that's a very broad goal. We're not there, but let's say we could do that. What are the benefits of that? Why is that? Does that have societal value? Well, I was preparing my talk yesterday and came across this article on the internet. And I think it motivated our research perfectly. And I did not coordinate with this author, but I appreciate him putting this article out right on time. So the New York Times has an article, "Buildings can be designed to withstand earthquakes. Why doesn't the US build more of them?" So this is a perfect question. So if we can estimate, or if we can calculate how strong shaking is going to be at sites, this article makes the case that we can build buildings that withstand them, those levels of shaking. That's tremendously valuable. That enables us to build a resilient society. So you put in extra money in the building where it's needed now. You don't strengthen buildings where it's not needed. But then you have the earthquake. The buildings continue to be useful, and they can function after the earthquake. So this is exactly the kind of research we do. People who build buildings, they need an estimate. What are the strongest ground motions going to be at that site? And so SCEC is one of the seismological, and we call it earthquake system science research groups that calculate and try and come up with these ground motion estimates needed by engineers. So another group, another still motivating it, who needs accurate estimates of ground motion. So this is another group. This is a plan called Resilience by Design. It's the City of LA's most recent earthquake preparedness. And in it, they talk about new rules in California for cell phone towers. And the rules have changed in the past, the towers had to be strong enough so they wouldn't fall down during an earthquake and hurt people. But now the rules have changed, the building codes, so that the towers need to be strong enough so they continue to work after the earthquake has happened. And that's a kind of emergency response. What are we going to all do? After an earthquake, we're going to want to communicate. And so having functional cell phone towers is very important. But now put yourself in the position of someone who builds cell phone towers. How strong do you have to make it? What levels of shaking do you need to prepare those towers in? So they can come to SCEC. That's the kind of research SCEC does. And we have been doing using Blue Waters. So this is an observation from working in the field. I'm on the computers side. I'm a computer scientist, so I don't identify as a civil engineer or as a earthquake scientist. But I'm watching these two groups interact, and I realize they're very different communities. So the seismologists don't follow the building code changes and the building code, the engineers don't follow what's new in seismology. But they do have communication channels. And as a software person, I think of these as basically a software interface or an API between the two groups. There are a limited number of kind of messages and communications that can go between these groups, but they are very well defined. And if you're a scientific researcher, and if you want to impact, so we're over here on the earthquake system science researchers, if we want to have our information used by civil engineers, we have to prepare it in a very specific way. We have to create one of these messages that basically civil engineers accept. And so these are examples. So I consider these the interfaces between the scientific world and the engineering world: site-specific probabilistic seismic hazard curves, and site-specific risk-targeted maximum considered earthquake response spectra. So these are the products. If you're doing earthquake research, if you want to influence the engineers, you have to prepare your results in these very specific forms and formats. And that's what we've been doing on Blue Waters this year. We've been calculating probabilistic seismic hazard curves for California. So this is a one-page description of these these data products. Probabilistic seismic hazard curves basically says what will be the peak earthquake shaking be over the next 50 years. You come up with there's a curve there. It's a site-specific. That's a key thing to remember, that each site will have a different curve. So the peak ground motions, expected peak ground motions differ site to site. And the map on the right is how they express it. It's a collection of hazard curves. And basically the red color means you're likely to experience stronger ground motions over 50 years in those locations. Now, one of the reasons this is important and Blue Waters is valuable to us is these are not static hazard estimates. So the USGS is a regulatory requirement to improve these. And it's typically every 5 years they need to come up, they need to review the science, integrate the best available science, and to come up with new estimates of the seismic hazard based on the current available information. So that's the process. This is an iterative process, updating these seismic hazards. So SCEC is developing new methods that produce better estimates, and there's a reasonable expectation that they'll be used in these broad impact national seismic hazard maps and in building codes, because both of those regulatory products need to get updated on a regular basis. So this year we worked on what we call the CyberShake, running a CyberShake hazard model for Northern California. So moving into 2018, our situation was we've developed a method using 3D-based ground motion simulations to calculate PSHA hazard curves. Our method is computationally intensive. So it's not currently part of the standard process. The USGS doesn't use CyberShake method yet, largely because they haven't had the resources, computing resources. But we've developed the method and applied it to first Southern California, and then to Central California. So in Southern California it was 2015, and Central California it was 2017. So starting early last year, we identified we should go to Northern California next. There's a lot of interesting seismological activity up there. It was 1906 was the last very large earthquake in California. The last damaging one was South Napa in 2014. So there's interest in the hazards up there. So we identified these squares kind of show, we started in the south on the black square as a Southern California hazard model. Central California is the purple, and then this year it was the larger Northern California region in orange. We identified sites of interest, so there's more, it's a large region, so there's more sites. There's over 869 sites. So one of the key inputs to these calculations is what we call an earthquake rupture forecast. So this is a list of all the earthquakes that are likely to occur. So it's based on where the active faults are, and USGS produces such a list of possible earthquakes that they call an earthquake rupture forecast. And so we use their USURF2 rupture forecast. Another key component is we call 3D seismic velocity model. This is basically a description of the geology and how fast the earthquake waves go through the earth. And it varies significantly from the surface, where the waves are slower, down to deep depths. The system involves setting up simulation meshes, something like this. So this is an example. A typical earthquake simulation would have maybe 6.4 billion mesh points. When you use these 3D velocity models, the characteristic of the seismic hazard changes significantly. The sedimentary basins amplify. The ground motions and the distribution of strong ground motion changes. In the existing methods, it's typically based, the ground motions fall off as you get away from the fault, but then you get these very kind of narrow hazard zones right along the fault, which are not considered accurate. One of the challenges for their Northern California run is that there's not just one 3D seismic velocity model in California, there's several, but none of them covered the full simulation region. So we developed a technique called tiling, where we combine them. So the white box here is the region where we need to mesh up and create a realistic 3D velocity model. And we assembled it from various elements. So a Central California 3D model, a Northern California 3D model, a Southern California 3D model, and then for some regions where we don't have information, we used a 1D background model. So we did conduct this simulation, and we called it a production run, and it was substantial. So it took, we distributed across both Blue Waters and Titan, and it took nearly 5 million GPU hours and 1.3 million, sorry, it's my 5-minute warning. If we break it down by, we used both CPU and GPU nodes on Blue Waters and GPU nodes on Titan. This is a long time. This took us 30-some weeks end to end to run this. And that's very challenging to keep a production run going that length of time, particularly with a small staff. And key to this capability was the ability to use workflow tools. So we used Pegasus workflow management and Condor HT and USC, and we're able to distribute the calculations very dynamically across the available computers. This type of automation through workflow tools is really what made these simulations possible. So for time, I'm not going to go through all of these pieces. But this shows that there were three basically centers involved: USC, where we have our meta scheduler running, and then dispatching jobs both to Blue Waters and Titan and FTPing files around. In the result, we end up with a hazard map like this. And so this shows on the left basically the CyberShake estimate of the seismic hazards, and the far right is the standard methods. And the center shows a difference map, a ratio map, where areas in red, CyberShake estimates the hazards are higher than the current method. And green is where the hazards are considered lower than the current method. So the science group are digging into this and evaluating sites of interest. I won't go through this, but one of the things to point out is that hazard estimates don't always go up. Sometimes they go down, and this can kind of suggest that these new methods don't only increase costs to buildings, but could also reduce building costs if hazards are lower and extra strengthening is not needed. The Central Valley San Joaquin is another area of interest, and the relation between the hazards and the sedimentary basin is being investigated. So at this point, we've moved the CyberShake method up the state of California and covered most of the densely populated areas. And there are indications there's building interest in using this technique and being adopted by the broad impact users. We've worked with and are currently working with civil engineers and have gone through the process. Here's actually how this research results will get into a building code, and I'm happy to talk about the details, but we have a collaboration with civil engineers from the American Society of Civil Engineering Society, who develops building code recommendations, and some of those recommendations will be based on these CyberShake results. As an example of how the scientists and the engineers are using these and working together, SCEC has developed a special information delivery website that delivers our results in just the form that the engineers use and need. So this is preparing our results in the format that the broad impact users require. So as I close, I'm going to mention that the SCEC Use IT program also benefited from Blue Waters. For 2 years, we've gotten awards and been able to give undergraduate students access to HPC on Blue Waters. That's encouraged our students interested in the geosciences. And I have a final slide here. I won't go through in detail, but kind of a summing up of the accomplishments in the seismic hazard research during the kind of the lifetime of Blue Waters. And there's been tremendous improvements over while Blue Waters has been operating, from the computational scale, code performance, improved physics, higher simulation frequencies, more verification, cooperation between resource providers, increased student participation, extending the method to new areas, customized data access for important end users, and interest from and use from broad impact user communities. All of these kind of improvements have happened during the time we've been developing these hazard products on Blue Waters.